Hi, Maria. Thank you so much for doing this interview. Before we start, may I ask you to briefly introduce yourself in terms of your background, research interest, education, and work?
Yeah, sure. So, thanks for inviting me to do the interview. My background is that I did a physics degree here at Oxford. So I did a kind of 4-year integrated masters in physics. And then in my 4th year, I did this project to do with quantum thermodynamics, and I became really interested in quantum information in general and quantum computing. And then I stayed with the same group to do a PhD. So now I'm in the 3rd year of my PhD at Oxford, working with Vladke Vedral in the physics department in the Frontiers of Quantum Physics group. And I'm also co-supervised by Arte Reckert here in the Maths Institute.
Cool. So you completed integrated master's degree in physics here at Oxford. Can you talk about your specialization during that time? What was your master's thesis about?
Yeah, so with the Oxford course, you start to specialize in the 4th year, and that's when I did a module on theoretical physics, a module on lasers and quantum information, and then the 3rd part was a project. And for the project, I got in touch with Chiara Marletto, who is a research fellow in the physics department, and we were working on a project to do with quantum thermodynamics. And so some of the things I was interested in and I'm still interested in are the laws of thermodynamics. So how we go from how we describe the arrow of time in a satisfactory way. And I was also interested in quantum information. I was also interested in the erasure of information and various paradoxes that seem to arise from that through thought experiments like Maxwell's demon. And so this project kind of brought those things together by looking at a new approach to the laws of thermodynamics, which is inspired by something called Constructor Theory, which Chiara has been working on, and applying this to a quantum model for erasing information. So I was doing some calculations trying to work out what happened with this model for information erasure, kind of with a set of qubits, and motivated by this new framework for expressing thermodynamics in an exact way.
So when we are talking about quantum thermodynamics, how would you explain quantum thermodynamics to a complete layman?
Yeah, so the field is very broad, but I can explain one aspect of it, which is kind of related to why I got interested in it. So one aspect is that all the laws of quantum physics are all reversible and symmetric with time. So anything that's allowed in a forwards direction is allowed in a reverse direction. In quantum computing terms, this translates to every gate you can always do a quantum gate that will reverse it. And this leads to a problem when you think about the fact that we've got irreversibility on a large scale. So we see eggs go from being unscrambled to scrambled, but we don't see them going from being scrambled to unscrambled. And so one way that people tend to explain this is through statistical arguments that an egg is more likely to end up scrambled than unscrambled because there's lots more ways for the egg particles to be scrambled than to be unscrambled. And so some people like to state the laws of thermodynamics using these statistical arguments, that the disorder or entropy of a system is unlikely to decrease. But some people would say that the laws of physics, if they're fundamental, they should be exact statements without probabilities in them. Ideally, like the conservation of energy is an exact statement. It doesn't depend on probabilities. And what we've been looking at is expressing irreversibility in a way that doesn't involve statistical arguments and probabilities. So using the egg example, instead of saying it's unlikely to become scrambled, we say that there exists a catalyst for scrambling eggs, like a whisk. You can reuse a whisk to scramble an egg over and over again. but there doesn't exist a reliable catalyst for unscrambling eggs. You need to put lots of resources in to do that.
Yeah.
And so you have this irreversibility where a task is possible, the opposite task is impossible to do in a cycle, even when all the dynamics are actually reversible with time. So yeah, in this project I was looking at a quantum model for this, so kind of looking at the equivalent of scrambling an egg in the quantum world, which is like turning a qubit from a fixed state to some randomized noisy state and back again.
Why are irreversible processes such an important concept in thermodynamics?
Yeah, irreversible processes. So one reason that they fascinate lots of people on a foundational level are that that's our kind of best explanation for why we see an arrow of time, is that we see this irreversibility from order to disorder, and we see things only going in one direction. So there's this kind of foundational aspect. There's also a very practical aspect to thinking about this kind of irreversibility, in the sense that if this law didn't hold, that we don't have to go from order to disorder, or we can go from disorder to order again, then one thing we'd be able to do, for example, would be in the air around us right now, there's loads of particles moving about really fast, and you might think, oh, maybe we could like harness the energy of those particles moving really quickly and use that energy to do something useful. And so you could charge your phone from the particles vibrating in the air, for example. And the laws of thermodynamics about irreversibility are what rules this out, because it says you can't turn the heat in the air into useful energy, which is work, which is what you need to charge your phone. So if there's a way to bypass the laws of thermodynamics somehow, or if this law doesn't kind of precisely hold in all situations, then there might be ways to harness new forms of energy that we couldn't harness without knowing those laws. So it has really interesting practical applications in that sense.
Right. So you founded the Oxford Quantum Information Society. Where the idea came from? How many members does the society have? And what society achievements are you most proud of?
Yeah, so in my... so I started the society in my 4th year of undergrad. Establishing the society kind of happened to coincide with when Google made the big announcement of like quantum supremacy in autumn of 2019, which was a kind of nice combination. And so the idea, I kind of had the idea towards the end of the summer before starting 4th year, where I found out about Qiskit, IBM's quantum programming language, and found these resources online where you could kind of teach yourself quantum computing using these resources. And what I was thinking at first was it would be cool to maybe get together some kind of regular group to work on these together, or to teach ourselves quantum computing together. And then I thought, well, I might as well make a society that has talks and other events as well, because there isn't that many events going on specifically in the quantum information field in Oxford. So that's where the idea came from. And then I kind of made this Google form to ask for committee members and sent that out to everywhere that I could think of online. And got an enthusiastic group of people together to run events. So yeah, we ran lots of events in the first term, which was fun, like quantum computing lab tours and flash talks from PhD students. So yeah, you said which event I'm most proud of or something, and I think I really enjoyed the flash talks, which became a kind of recurring event in other terms and in the future when I left the committee as well. So because we'd have like 3 PhD students each talk for 10-15 minutes about their projects, and then in a short amount of time you find out about loads of different stuff that people are working on, which was fun. And in terms of numbers, in the first term we got over 100 people kind of registered,
Wow.
which was nice. There's lots of enthusiasm there. And I'm not sure what the membership number is now. I'm not on the committee anymore. But one thing that did happen is when we went into lockdown, a new committee took over and was running events online, posting them all on YouTube. And that led to, I think, a lot of people outside Oxford joining as well. And so now the Facebook page has like over 3,500 likes. And I think people have, people outside Oxford kind of started to get it, to see the events and join in, which is nice as well. Now there's a kind of mix between in-person and these online ones. Yeah.
So you are a PhD student here at Oxford. What is your main research interest and your PhD topic?
Yeah, so one of my projects is kind of carrying on these ideas I was working on in my master's. So developing this quantum model for this kind of irreversibility that I talked about. Some other projects that I'm working on, I'm interested in various quantum thought experiments to do with reasoning about observation. So one of these is, so there's a few different paradoxes. There's Hardy's paradox, which was proposed a while ago in the 90s. There's the quantum pigeonhole paradox. There's the Frasch-Renner paradox. And these various paradoxes were kind of proposed at different times, and they all involve some kind of doing some measurement, quantum measurement of some kind, and then drawing conclusions about the outcomes of these measurements. And what I find interesting is looking for kind of connections between these three and similar thought experiments, and seeing if we can kind of unify the way that we're thinking about all of them. And can we say that the problem in one of them is the same as the problem in the other one, and that we can resolve them all the same way? And ultimately, I think the conclusion is that quantum theory is actually fully consistent when you take into account of the nature of what a measurement actually is properly. But sometimes it becomes quite subtle when you introduce observers that you can, then you try and model them quantum mechanically and various questions arise. But ultimately, everything is consistent. We don't have any known problematic paradoxes of that sort, I think. But yeah, there's still a question of trying to work out exactly how to best show that.
Can you explain what is a constructor theory?
Yeah, so constructor theory is a research program that it was originally proposed by David Deutsch in around, he wrote a paper on it in 2012 on the philosophy of constructor theory. And the, one way of thinking about it is that it was generalizing the theory of quantum computing. So instead of imagining a universal quantum computer that can simulate anything that can be simulated, a universal constructor could perform any task which is allowed by the laws of physics. So as well as doing things like computation, it could also, for example, do self-replication, if that's possible by the laws of physics, or heat up a glass of water, for example. And so that's the idea of a universal constructor, which would be the kind of ultimate form of technology in some way. But the aim of the theory as a whole is actually to formulate the laws of physics in terms of what transformations are possible and impossible and why. And by framing the laws of physics in this way, the aim is to be able to express laws about information and quantum information in an exact, unified way, because it's difficult to state laws about information just in terms of dynamical laws. And the other aspect is to explain the laws of thermodynamics in an exact way. So, yeah, like scrambling an egg is possible, unscrambling is impossible, and having these exact statements to state those laws. And and then you can end up with a theory of constructors as well. So constructors are essentially catalysts for doing tasks.
Mhm,
So we say that a task is possible if there exists if the laws of physics place no limit on how well you could reliably do that task. And to formulate a theory of these constructors, we need to understand what the laws are about what's possible and impossible.
Right. So what would you say are the most interesting quantum paradoxes?
The most interesting quantum paradoxes, I think one of the most interesting quantum thought experiments that seems paradoxical, but in reality, none of them are truly paradoxical when you look into it. But one is the quantum bomb tester thought experiment. So this was proposed by Avshalom Militzer and Lev Weidman. So some people call it the Elitzer-Weidman bomb tester. And this involves looking at a problem where you have a box and you don't know what's inside. It may or may not have a bomb inside, and this bomb is sensitive to a single photon, or any interaction will cause it to explode. And what you have to do is work out whether or not there's a bomb in the box without it exploding. And so classically, there's no way to do this, because if you try and see if there's a bomb, then it will explode. But you can use a quantum setup to work out that whether or not the bomb is there without setting it off, which is really amazing when you think about it. And especially when you think about the setup that's used. So it uses a kind of single photon that you send to a beam splitter to split into two paths, and then it merges into one path again. And what you do is you put your box into one of these paths, and it either causes the photon to collapse and explode the bomb, in which case that's not the outcome you want, or it can collapse into another branch and not explode the bomb, and then you have a chance of detecting the bomb was there without setting it off. And I think that really captures some of the strange aspects of quantum mechanics.
Right. So you were a quantum engineering and education internet Hrvoje. Can you talk about the projects you worked on and what was that experience like for you?
Yeah, so I did an internship at Hrvoje in the summer of 2020. So that was between my master's and PhD. And the aim kind of going into it was to make something that's a kind of education themed project that we can use to explain to people about Hrvoje's quantum operating system for quantum computers. So what I was doing is, so the aim was to explain this operating system that they have called delta flow, which was, meant to kind of be installed in a quantum computing lab, and then it can control the different aspects of the quantum computing lab so that everything works together efficiently. And what I did was make this network of Raspberry Pis and other circuit boards, and then connect them together with wires, program in them being able to kind of communicate to each other, and then program in this operating system that Hrvoje were working on for quantum computing labs onto these circuit boards. So one Raspberry Pi was running Qiskit as a quantum simulator. So that was the kind of quantum hardware Raspberry Pi. Another Raspberry Pi was like the lab computer, which is where you'd program your algorithm on a high level. And then in the middle, there was some circuit boards representing something called FPGAs, which are kind of used in a quantum computing lab to control the hardware. What you could do was, what I programmed it to do was a Rabi oscillation, which is to have like a single qubit and then observe it oscillating through different quantum states. And so, this involved kind of, you program your lab computer, and then you have this feedback back and forth between the circuit boards and the quantum hardware, and then the message gets sent back to the lab computer. And at the end, I kind of pulled this together into a video which explained the setup, and then we put that on on the Riverlane YouTube and on this STEM Ambassadors YouTube channel, which was kind of, aimed at engaging young people with quantum computing.
Cool. So you also created a quantum startup called Rescue using quantum machine learning. What was this project about? And can you explain the technical side of quantum machine learning used in this project?
Yeah, so this was a quantum startup concept that I made with a team as part of an initiative called Quantum Entrepreneurship Laboratory, which was run by an organization called Push Quantum, which is based in Munich. But because it was all virtual, I joined virtually while I was in Oxford. And there was like a group of, I think, 20 of us, and then we were in different teams working on, each working on a different startup. And then, so my team was working with Eon, so they were our mentor, and what we were doing was working on a project idea to use machine learning to classify the resilience of the electricity grid. So the aim would be to use this information to kind of prevent blackouts and make sure that energy is distributed in the right way across the grid. And our product would take in data about the electricity grid and provide kind of live updates on the resiliency of different parts of the grid and which parts kind of needed attention to prevent a blackout occurring, for example. And so on the technical side, what we were using to classify the resilience was a machine learning algorithm called the support vector machine. And what this does is it kind of maps the data you have onto a kind of different space where you can separate it into two parts, where we have the kind of resilient and non-resilient part. And we kind of used this to find a probability score of like how likely is it that this data corresponds to a resilient to the resilient side as opposed to the non-resilient side. And the way that quantum algorithms can help with this is that one part of this support vector machine learning algorithm is working out this mapping from your data to this space where you separate out the kind of resilient and non-resilient data points. And that mapping can potentially be accelerated using quantum algorithms. So we used this quantum version of the machine learning algorithm and also made a classical version. And the aim was to develop those to build this product.
Cool, perfect. Can you talk about some of the new developments in quantum science?
During my PhD, I joined the Physics World Quantum Student Contributors Network, where we write articles on latest news updates in quantum. And I've been able to cover some cool stuff. So one of them that you mentioned was using quantum error correction for astronomy, where some researchers made a proposal where you can when you capture starlight with a telescope, you can convert that onto a quantum system where you can use a quantum error correcting code to protect that information in the starlight from outside noise. And so, what quantum error correcting codes do is they use a redundancy of having the information kind of copied in lots of ways to protect it against errors happening. And you can then correct your system to make sure it stays in the space that you want it to stay in. So yes, that was really cool. It lets you have your telescopes be kind of further away from each other, so you can create higher resolution images using these. And it could also be something that could be done with near-term quantum devices, because it doesn't need the kind of really high accuracy that quantum computing applications need for quantum error correction. So that was really cool. Another one that I covered was to do with creating a nanoscale clock and understanding how that relates to entropy creation, which is a measure of disorder. So that was a kind of quantum thermodynamics themed experiment, which involved researchers at Oxford, including Natalieri's group, and that was kind of investigating how the precision of how closely you measure time showed that has a kind of minimum entropy cost to the environment, and investigating that for this experimental nanoscale clock. And then another news piece that I covered was the first fault-tolerant control of a single qubit. So that was done by some researchers in Maryland on using an ion trap qubit, and the aim there was to again, relating to error correction, you want to encode the information of a single quantum bit into a lot of physical quantum bits, so that if there's an error, you can detect it and correct it. And they showed this control for a single qubit, like applying quantum gates and so on, all in this protected way. And it's been pretty cool that since then, there have now been people demonstrating that for 2 qubits and 2 qubit gates, and also, showing that you can get kind of good scaling with adding more qubits. So it's been cool to see the developments since that news story.
You work as a quantum computing intern at IBM. What is your role as an IBM quantum community advocate?
So with IBM, I've been doing this part-time internship for a while now, working with the video team. So I've been working with the Qiskit video team to develop content for their YouTube channel, and also working with the writing team to create blog posts. And sometimes I've been involved in other community events, such as the Qiskit Global Summer School, which I gave some lectures for the summer school on Hamiltonian simulation last year. And so the main part of my work is creating these videos about quantum paradoxes, where I've covered the bomb tester and Hardy's paradox, pigeonhole paradox, and some of the others that I mentioned. And I'm planning to do some more of those. That's really fun. And I've also been making these 1-minute Qiskit videos, which are short videos explaining tips and tricks with Qiskit, alongside another member of the community team, Frank. And we kind of developed that series into a fun Qiskit bot battle for the we did a 12 days of Qiskit event in December, which was a kind of a live coding thing where we'd do a different live coding challenge each day, and we did a live coding battle between us. So there's lots of fun content that we're making there.
Since you are an experienced Qiskit user, would you say that it is the best quantum software development kit, and why?
I use Qiskit a lot. I'd say I can't really comment on whether it's the best one without kind of properly using other ones too. But I think one thing that the Qiskit community does really well is having really good accessible resources for getting into quantum computing or starting to learn quantum coding. I think that's why I started using Qiskit, and that's why even before I was working for Qiskit with this internship, I was kind of recommending it to people to look at those resources. The Qiskit textbook is really good. It has this kind of scratch pad thing where you can like code as you learn, which is good. And there's lots of kind of examples on the YouTube channel there's 2 seasons of coding with Qiskit where you can learn to code quantum algorithms. And I think because it's based on Python as well, which is a really nice to use programming language, that makes it accessible to do to get into to programming quite advanced things pretty quickly. So
What do you think about physical implementations of quantum computing? Who is leading the race at the moment?
Mm-hmm. Yeah, so I think so the main physical implementations that people have been focusing on are one is superconducting qubits, which places like IBM and Google have been focusing on, and they've kind of got the most qubits for universal gates. So yeah, IBM recently released a computer with I think it has over 400 qubits. So they've got a lot of qubits with superconducting. Another kind of front runner that people think about is ion traps. A lot of people are working on that and have ideas for kind of scaling up ion trap quantum computers by kind of connecting them in various ways. But some people also think that other implementations might prove better for like making really big quantum computers. So there's some spin-outs and companies working on photonic implementations of quantum computers, and they are kind of they think that for a really large quantum computer with loads and loads of qubits, it would ultimately be better to build on a photonic platform. So in terms of me personally, I don't know which one will actually turn out to be the best, but I think it's worth exploring all the options that look like they're serious contenders for building a quantum computer. And I imagine that all of the research and development that we do in all these promising platforms will end up being useful and contributing to the overall goal of doing something useful with quantum computers. And it might be that certain platforms end up lending themselves to certain applications. I think exploring all of these in parallel is really good.
Right. What do you think about artificial intelligence? Do you believe it will be more powerful in 50 years' time than quantum tech?
So 50 years' time is a pretty long time. I imagine that things will be completely transformed in a lot of ways by then. Maybe even by something that we don't know right now. Instead of AI and quantum, maybe it's something entirely different. But so I kind of see, I think AI will have a really impactful effect on the future. We've already seen kind of really powerful platforms like ChatGPT has enabled loads of new ways of interacting with AI and helping it speed up things that we do in our day-to-day lives. But I see AI and quantum as having impacts on kind of different streams of what we do. So AI has kind of already shown useful things for lots of applications, and people are developing that. Quantum, we're still trying to reach that milestone of using a quantum computer to do something useful. But the quantum computers open up an entire space of things we can do efficiently, which we can't do with a classical computer. However good the AI or software that we have is, there's a space of things that we can't access without a quantum computer. So I think inevitably we're going to have to sooner or later build quantum computers in order to access the space of all the things that we can do. And to get these advantages which people think we can get in drug discovery, for example, by simulating molecules much more efficiently than classical computers, we're going to have to build quantum computers and see how to do that. So I imagine them kind of working together in a stream where if we can get to a useful quantum computer and develop that, then we suddenly have loads of things that maybe we could speed up with AI, or maybe we could use some of these quantum algorithms to speed up some aspects of AI. And I can see lots of potential for interactions there in the future.
Who is the greatest quantum physicist of all time?
The greatest quantum physicist. It's a difficult question, especially as sometimes you end up finding out historical facts about quantum physicists,
Yeah.
which make you not really want to say that they're that great necessarily.
Yeah.
But maybe I could tell you about a paper that I really like.
Yeah, sure.
So one quantum paper that I think is really cool is the paper that introduces the no cloning theorem.
Okay.
And the reason I like this is because it's a really fundamental result that you can't clone quantum information, whereas you can clone classical information, which makes this kind of surprising. But the paper is it's really short. It's just like a couple of paragraphs, and this derivation of the no cloning theorem is really short. It's just a few lines. It kind of drops out straight from the formalism of quantum mechanics. So I really like the fact that such a simple idea can have a really big impact on the field, and no cloning kind of it's what prevents faster than light communication happening, for example, and it has lots of fundamental implications for understanding what we can and can't do with quantum information. Maybe that's why I also like science communication, is kind of doing the same thing of trying to explain things in very simple ways, but still see them as having a big impact in a field. So I think that paper is really cool.
Right. And last question, what skill set every successful entrepreneur has to have?
So I haven't founded a company myself, so it's so I can't exactly say from experience as such what a successful entrepreneur should have. But from attending various entrepreneurship courses and projects, and I've been working with the MPLS, Mathematical and Physical Life Sciences division here at Oxford, as an Enterprise and Innovation Fellow to try and kind of organise events around entrepreneurship. I've talked to various people who have founded companies or have given advice on it, and from that, what I'd say that I've learned from people seem to be the driving factors of being a successful entrepreneur. One of them is having kind of drive and ambition to do something, and that's what's going to kind of propel you through the difficult times, is having a vision to do something. Also being resilient to failure and open to failure. So I think you have to be open to kind of failing again and again and again, and having that as an option, and not being put off by failing. And that seems to be that resilience seems to be one of the most important things to have as an entrepreneur.
Perfect. Is there anything else you would like to add at the end for our viewers, perhaps?
I'd say to the viewers that I think quantum science and technology is really exciting space. So I recommend browsing the web or YouTube or anything and finding what kind of things you think are cool and looking further into it. I'm sure you'll find something that you find really interesting.
Perfect. Maria, thank you so much for this conversation, and I wish you all the best in your career.
Yeah, thanks for inviting me. It was fun.
Thanks.
Yeah.